Hello, Honors Chemistry, and welcome to the Chapter 7 review, where we are going to work through the problems from the practice quiz so that we can hear all the stuff spelled out one more time, which might be helpful to you as you are reviewing or working through this quiz, wherever it is that you are. All right. So, for starters, what you should have out is your practice quiz. Whether it is you're checking it or you're just listening to this, it's helpful to have that out in front of you. In addition, obviously, your periodic table. And then, obviously, anything else you've not memorized yet but are supposed to be working on, like solubility rules, polyatomic ions, all that good stuff. All right, so for starters, it says that aqueous solutions of lead acetate and aluminum sulfate are mixed, and we should provide a net ionic. So first, let's go ahead and write formulas for each of our reactants. So lead 2 acetate, right? So again, that 2 is the charge of lead. So we know this is Pb, and acetate is C2H3O2, and there need to be 2 of those because that has a charge of -1, and I know it's aqueous. My other reactant is aluminum sulfate, right? Aluminum has a charge of +3, sulfate has a charge of -2, so 6 is our lowest common multiple, and so we're going to do that, aqueous. And if as I'm saying that, you're like, oh, that's all so fuzzy, then you should go back and watch the Chapter 5 review stuff first to refresh your memory. All right, and then what we're going to do, like we said, 2 aqueous ionic compounds. Let us switch the cations, or just 2 ionic compounds in general. Switch the cations, so aluminum will now be stuck to acetate, and we have to reason through that formula again, right? Chapter 5 rules first. So that would be aluminum, and then C2H3O2, aqueous, or well, we'll wait on the state, but there need to be 3 of them for the charge, right? And then we know that lead will be stuck to sulfate, and it's going to keep that charge, right? There are reactions where it changes. We're going to simplify and say we're going to stick to the land where they don't, and we'll put a state there. Now we need to apply our solubility rules, which tell us that acetates are always soluble. So this one is going to be aqueous because there's water in the background, courtesy of these aqueous reactants. Lead sulfate, we would look at our solubility rules and think, sulfate, usually soluble with a handful of exceptions. Lead is one of those. So then this is going to be a solid, right? Which means that that's going to be our precipitate. So in order to get to the net ionic, what we got to do is we've got to work our way through here and cancel all the things, right? So this is aqueous, it is ionic, so it's going to dissociate into its respective ions, right? So we have, we got to balance, right? So we have 2 aluminums and none, so we'll put a 2 there, which gives us 6 of those acetates, so we'll put a 3 there and a 3 there, and we're balanced. So to work down to our net ionic, we have 3 Pb2 plus ions that are aqueous. We have 6 acetate ions that are aqueous. We have 2 aluminum ions that are aqueous. And we have 3 sulfate ions that are aqueous. Then on my product side, I've got 2 aluminum ions that are aqueous. I've got 6 acetate ions that are aqueous. And I've got 3 PbSO4 solid. It is not aqueous and ionic. It does not dissociate. It stays stuck together. Then we'll go through and cancel out the things that are exactly the same on both sides, right? We got these 6 acetates, my aluminums, and everything else becomes my net, right? So my net is going to say that I have 3 Pb2 plus aqueous plus 3 SO4, 2 minus aqueous is going to give us 3 PbSO4 solid. Note here, right, that it is reducible, right? So in the best case, we would then take 1 of each, and that would be our final answer. If, like it says in the answer key, if you were to give me the ones with the 3s in it, I would take that for full credit, and that's fine. So we write the complete molecular, we then do our complete ionic, and then we cancel the spectators to come to our net ionic, which is a representation of what actually changes, right? So during the course of this reaction, we consume lead ions, we consume sulfate ions in the production of this lead sulfate solid, right? Everything else stays the same, right? All those other ions were floating at the beginning, the lead and the aluminum and acetate ions, and they're still floating around in the end. There is no change to those components. All right, next up, it says we have aqueous solutions of sulfuric acid and sodium hydroxide, and they are mixed, right? So same thing, let's come up with some formulas. Sulfuric acid comes from sulfate, which has a charge of -2, which means H2SO4, aqueous, plus sodium hydroxide, so that would be our NaOH, and it tells us it's aqueous, right? And then here we'd be like, switch the cations, right? And so sodium will now be stuck to SO4, which means I need 2 of them, right? And then H and OH give us water, okay? And sodium sulfate, sodium is group 1, so always soluble. Then we just have to go through and balance, and we would be done, okay? Now, just like last time, in order to get to the net ionic, we will ask ourselves, is it aqueous and ionic, right? And going back to your lecture notes, acids, we're going to treat them as ionic compounds. So in this case, I'm going to have 2H plus aqueous. I'm going to have my sulfate aqueous. I'm going to have my 2 sodium ions aqueous and my 2 hydroxide ions aqueous. And then I will have 2 sodium ions aqueous. I will have my sulfate and my 2 waters, which will stay stuck together because they are not aqueous and ionic. Then we'll go through and we will cancel the things that are exactly the same on both sides, which would be our sodium ions and our sulfate ions, and everything else becomes our net, right? So 2H plus 2 hydroxide gives us 2 waters. And again, we see that it is reducible, right? And so we could do this plus 2, nope. The point was to get rid of those. 2 hydroxides, or 1 hydroxide aqueous, to give us our 1 water. All right, fantastic. Now, next up, it says liquid benzene is combusted. So, and again, you're not expected to know these formulas. I would give them to you, right? So C6H6 liquid is combusted. That means reacts with oxygen. And don't forget, combusted could have other terms like is exposed to a flame, is exposed to a fire, is exposed to a spark. Any of those things would mean the same thing as combusted, and which means we're going to make CO2 plus H2O, right? And don't confuse the fact that we have combustion of a hydrocarbon, so like a CH or CHO compound with oxygen, right? Or we have those other reactions where it's an element plus oxygen, which is a combustion, but it's also the type of reaction where we have 2 elements and really we're just going to make a compound, right? Note that when we have 2 elements, there is no concept of switching. It's not even possible to make CO2 and H2O because you don't have enough elements to get that done, right? Does that make sense? So yeah. All right. And then the only trick would be this would be gaseous because we got all that whole exothermic heat thing happening, right? And then we just got to balance, right? So C6, so I would put a 6 here. H6, so I would put a 3 there. And then I would say, oh no, that gives me an odd number of oxygens, right? And then, so then I will go fix that odd number by putting a 2 here, and then a 12 here, and then a 6 here, and that gives me 24 plus 6, which is 30, which gives me 15, right? Note that alternatively, right, in your book, what your book describes is using the fractions to figure it out, right? Wherein if I started with what we had before, right, so this would be 6, this would be 3, right? And when I add these, right, that's going to give me a total of, 12 plus 3 is 15, right? So in order to get the right number of oxygens here, really what I need is 15 over 2. And then what we do is we go through and we take everything and then we figure out how to scale to get rid of that 2, right? Which would mean times 2, times 2, times 2, times 2. And that would also get the job done, and you'd see we get the same answer we got the alternative way, right? Whatever way makes more sense to you. I know that most people, fractions are not the preferred option to work with, and really it's just a matter of fixing the odds and evens, which I think makes sense to most people. All right, next up, copper 2 oxide, right? So that's CuO. Solid because it's an ionic compound and there's no water present, and it's made of 2 elements, so the only option is to decompose it or break it down, because that's what decompose means, right? Break it down into its 2 respective elements, right? Copper, which is a solid because it's a metal, oxygen, which is O2 because it's diatomic, and it's a gas. And then we would go and balance, right? Note that decomposed should not be confused with the term combusted, okay? All right, next up, potassium sulfite is added to aqueous hydrobromic acid. So without any other words, this potassium sulfite is an ionic compound, not already in water, so it's just going to be K2SO3, right? Solid. Aqueous hydrobromic acid, so HBr, aqueous, right? And then we look, let's switch the cations, right? And then we would have KBr, because it's a charge of +1, -1, right? And then this would be aqueous, because group 1s are always soluble. And then we would have H stuck to SO3, which would give us H2SO3. And then we would say, that's right, H2SO3 is always going to spontaneously and pretty much instantaneously decompose to give us H2O and SO2. And then we would go back through and we would balance, and then we would be done. All right, next up. It says aqueous solutions of lithium chromate and ammonium nitrate are mixed, right? So again, charges, right? Lithium chromate, that's a 2CrO4 aqueous, is mixed with ammonium, NH4, nitrate, those are all ones, so this aqueous. And then we're going to switch our cations, so NH4 will now be stuck to the chromate, and then this is our always soluble list, and then we'd have lithium nitrate both on our always soluble list, and then we would go back and we'd balance and we would be good to go, right? So again, like I've emphasized before, right, simply knowing all the species on the always soluble list will get you the right answer more than half of the time, right? Because here, if we look, right, always soluble, which means that even after we switch them, our products are both going to be soluble. So then if this asks us as a follow-up for a net ionic, what that means is that we had 4 different ions present at the beginning, and we have those same 4 ions swimming around in the solution at the end, and there is no net change in our reaction vessel. All right, sodium is exposed to oxygen, right? So here we have sodium, the element metal, oxygen, the diatomic gas. This is one of those reactions that could be doubly classified as combustion and 2 elements reacting, right? And all we're going to do is put them together, right? Sodium has a charge of +1, oxygen has a charge of -2, so Na2O, ionic compound, no water present, so it must be solid. And then we would go back through and we would balance, and that would be it. All right, calcium is added to aqueous potassium phosphate. So we have calcium, it's a metal, so it must be solid. Potassium phosphate, so that's +1, -3, and it says it's aqueous. And then we would say, this is now 2 ionic compounds, but now we have an element and a compound. The element will switch with what it's most similar to, right? So calcium's a metal, so we're going to switch it with the metal, right? That's the simplest thing, that makes sense. So then calcium and phosphate are stuck together. Calcium has a charge of +2, phosphate has a charge of -3, so Ca3PO42. State, that's right, phosphates are typically insoluble, except for those always solubles, right? And then potassium would be our new metal, right? And then we would simply have to go back through and balance, right? It says we need 2 of these, so that would mean 6 of these and 3 of these. All right, next up. Silver is added to aqueous nitric acid, right? So we have silver, the metal, HNO3 for our nitric acid. And then we would, element plus compound. So the element, silver, will switch with whatever it's most similar to in the compound. Our options are hydrogen or nitrate, right? Because this is nitrate, not like nitrogen and then oxygen, right? Our options are either hydrogen or nitrate. And in terms of what it's most similar to, right, we might be tempted to do some weird comparison here, but hydrogen plays the role of a cation. So if we have to choose, right, which of these it's most similar to, it's going to be the hydrogen, right? Because hydrogen plays the role of a cation, just like a metal would, right? So then we're going to have AgNO3, because Ag has a charge of +1, so AgNO3. State is aqueous because nitrate's on that always soluble list, and H2 gas, right? Which means I'd put a 2 here, 2 here, 2 here, and we'd be done. All right, next up, write a balanced equation that produces chlorine. It doesn't have to be the only product. So here, what I would do is I'd start by thinking to myself, what is chlorine, right? Chlorine is an element. Then I would look through all my types of reactions or scroll through them in my head and figure out what type of reaction can produce an element. And the simplest thing would be the binary compound decomposes, right? So I just have to come up with a reasonable formula that has chlorine in it, sodium chloride, and then I would decompose it into sodium and some chlorine, and then I would call it a day. That would be the easiest thing to do, right? Similarly, another thing that produces an element would be one of the element plus compound, right? Element plus compound, where if I wanted to make Cl2, right, Cl would have to be stuck to something, right? So NaCl, for example, right, plus some other what? Right, in this case, it would have to be some other halogen, right? Could do the displacing, right? So we could say fluorine, for example, right? Plus that would give us Cl2 plus NaF, aqueous, right? And then we would balance accordingly. And then we'd be done. Yes, does that make sense, right? Whereas if it were like a compound or whatever, I would basically look for what types of reactions produce that kind of thing, and then I would work backwards, making sure all my formulas are reasonable. All right, that's all we got. This is chapter 7, and again, go through here and look at your types of errors, right? If all your errors are traced back to chapter 5 stuff, then that's what you need to be focusing on, right? Or if it's traced back to just getting your polyatomic ions wrong over and over again, that's what you need to be reviewing, right? If you're not sure, it is possible. You just need to review everything, right? That's a possibility, right? If you're not sure, feel free to bring your practice quiz by and I can look at it and we can look at it together and see if there is something we can pinpoint to help you target your studying. All right. Thank you for listening. Be good and I will see you soon. Bye.